Hello, and welcome to the part 3 of our video tutorial on how to master secrets of asynchronous programming. In the previous two parts, we set up the stage for the approaching the modeling of the real-life processes by recognizing that they are not controllable in the sense that we can freeze any processes that we don't want to keep going while we complete the computations and the processing that we are focused on, and only after we are done we unfreeze the other ongoing processes and continue with our logic. Today we are going to look more closely into some of the issues that are surrounding this concurrent or parallel or asynchronous programming, because in the previous presentation we showed how unrealistic and naive is the sequential, single-threaded and blocking processing, as it ignores the nature of the reality. So today we are going to tackle this outstanding question, which is how to switch from continuous execution, a sequential synchronous programming, switch over to discontinuous execution, which is the basically asynchronous or concurrent programming. We do that. One of the ways to do it is we can refactor our code. So if our code is some kind of a legacy imperative implementation, and it is just kind of marching from beginning to an end, blocking on the way as things have to happen, we now need to break it down into kind of two separate concerns. One would be the before block, before we reach the input-output boundary, and the after block. So here's the very basic refactoring that we can do. So, we can have a before and after version of our code, and then we try and get them to work together. And now we are going to walk through some of the ideas behind this approach. The before code would be responsible for any computations that happen before our processing reaches the I/O boundary. If you remember, we mentioned in the previous presentation that so long as our processing is happening in a single location, meaning it is located in a particular computer block of computer memory or RAM, we don't need to worry about issues such as latency, consistency, and shared mutable state. But if we have the need to get something done by having two or more processes collaborate, then they will be doing that across the I/O boundary, the input-output. The communication is happening at that level, and we need to break the code into the block that is doing computation before we actually hit the I/O boundary. When we actually hit the I/O boundary, so we have prepared all the information, and now we have to actually do some kind of input-output, be it listening on a network or sending something over the network and waiting for the response, connecting to some auxiliary storage to a database, or waiting on user gestures, etc., etc. The before code now needs to stop blocking. As we said, relinquish control, give up, take it easy, pass the control over to the process on the other side of the boundary. This is very important. So the before, another thing that is important for the before code is when it passes the control over to the process on the other side of the I/O boundary, it also needs to pass the callback instructions. And this callback will be used to notify the after process that the computation is complete. So while the process on the other side of the boundary is chugging, this before block of code that we labeled as before is now free to do other useful work. It doesn't have to idle, or it doesn't have to be fully occupied doing nothing. It can go and serve other requests and what have you. Now, once the processing on the other side completes, the notification is sent to the aftercode, the callback, which, just symbolically represented by this icon. And then when the aftercode or the callback code receives notification that says, okay, I'm done here, you can go and do your whatever your logic dictates, then the block of code that we label after will continue the processing from where it was left off during the before processing. So there's this kind of discontinuation or breakage in the sort of sequential processing. So far, so good. I think it is clear that this how this discontinuation is designed. And I don't think there shouldn't be any confusion regarding that. So when we accomplish that and we look at what we've done, we realize that things are looking great now because our processor thread is not blocking, it's not hogging resources. And therefore it becomes scalable, becomes very responsive because there is no latency, and scalable because it can now take more incoming calls that happen simultaneously because it's not actually in a holding or waiting pattern. So we pat ourselves on the back saying, okay, look, we removed the bottleneck, we are in great shape, good job everyone, fantastic. And we realized that this discontinuous execution model actually rules, and we all of a sudden were like, oh, what possessed us to be so fetishizing about this continuous sequential execution when discontinuous saves so many problems for us? And if that's the case, so we reach this point, we're asking ourselves, so why don't we now switch 100% wholesale, abandon the continuous execution model, and switch over to discontinuous execution model? And, in some platforms and frameworks, for example, I'll just bring up one example, Microsoft C#, where this realization came with a significant modification where it allows developers to use the await keyword, which will do all this behind-the-scene magic in refactoring the code into before and after blocks. It is given to the developers at no cost, and it's becoming brain dead easy now to abandon wholesale 100%, switch over to discontinuous execution. Now, it's kind of too good to be true, and anytime we get to this point where everything seems so fantastic, we have to slow down and ask, well, is there any reason why would someone want to stay with a synchronous continuous execution model? Because this model implies blocking the process at the IO boundary and latency and all these other issues. So do we really think that it is safe to switch 100% over to the discontinuous execution? And once we start looking into that, we realize that there are maybe a couple of reasons for staying with the synchronous blocking model and not just jump headfirst into the asynchronous. For example, we've mentioned earlier the shared mutable state, and this shared mutable state is a fact that remains. Just because we use the await keyword in C#, for example, doesn't mean that shared mutable state magically disappears. It's still there, and it still could be a problem. As a matter of fact, some people claim that shared mutable state is the root of all evil, which may be a bit of an exaggeration, but sometimes when you have those nasty bugs that you just cannot reproduce or easily troubleshoot and fix, you get to that point when you think maybe it is the root of all evil after all. So if two or more processes or threads share the same mutable state, then basically it is anyone's guess if and when that state is going to change, because they're running in parallel and there is no crosstalk between them or synchronization. And in that arrangement, if a before process holds on to a shared mutable state, relinquishes the continuous execution model, and the shared mutable state may or may not be the same as the state that was computed before the execution got relinquished. So that is the potential risk that we are definitely incurring when we are moving away from the blocking and sequential execution and moving into the discontinuous execution while at the same time handling shared mutable state. This is a very serious concern. So this may sound a bit theoretical, and maybe it's easier if we just walk quickly through a hypothetical example. And this is going to be very, very simplified, but hopefully will clear some of the potential questions. So let's say an online customer is doing shopping, putting items into a shopping cart, and decides to go to the checkout. So say, okay, I'm done shopping, I want to buy. Before the customer can pay for an order, let's say that the system needs to prepare something like the customer service agreement document for the customer to sign. So it's not just a straightforward, okay, I'm paying for this and it's going to get shipped to my home address. There's a bit more involved in that. We need to also agree on some service agreement. And, this thing needs to be prepared, sent for signature, and could be fairly elaborate sometimes, depending on what the store is offering and what the customer is buying. And to prepare that document may actually take a few seconds, sometimes even a few minutes to prepare. And that's understandable because there's probably a lot of things to go in the back and reach into some services and get enough specific information to prepare the document, which, if we're doing sequential imperative programming would lead to blocking, because now we are hitting the I/O boundary, the system is going into reaching out to other services, and that blocking will actually be undesirable because we are hogging resources. Other calls may not come through. Therefore, this order processing thread will switch to the async mode, discontinuous execution. And before switching to the async mode, the order processing thread will remember the state of the order, meaning there's a list of order items, the quantities, prices, etc. So everything is kind of remembered because it's now relinquishing control. And after a while, this latency kicks in and is happening, taking a few seconds or maybe a minute or so. Eventually, the document is ready, is complete. And then the document service notifies via a callback, the after process, that everything is ready now, you can continue with your regular order processing. So now the after process takes over and sends the notification to customer that, could you please go over this document and agree with the terms of services before you can actually complete your purchase. And then it takes the customer to the checkout page. The checkout page will now present the customer with the order details as those details got remembered by a thread. All the order items, quantities, prices, order total, all the regular stuff. So far, so good. Makes sense. It's all logical. But there's something could be potentially wrong with this picture. And, sometimes we are dealing with the unicorn and the unitard on the unicycle. It's it's kind of a fantasy world, because we have now stepped into a minefield called latency. Latency is troublesome because in real world we cannot press the pause button while doing all these acrobatics in the background. And while another process is working on generating service agreement document, our code is now assuming that nothing changes, everything is frozen. This is a naive assumption, and of course it is not realistic. And the question now is, what could possibly change while we wait? And certain things can quite easily change. Maybe prices on any chosen item might change during this latency also. Since the order processing thread has relinquished control, it's now frees up the customers to go and continue shopping. Maybe a customer wants to add more items to the cart, or may want to remove some items from the shopping cart. All that while the document is getting prepared. So the customer we want the customer to, of course, do some more shopping because it's in their best interest. And these things mean that the final order being processed by the after block of code may calculate incorrect totals and may be presenting customer with the order that is not correct, does not reflect the reality. Which basically, as we've seen in many like real-life examples, the switching to async programming can quite easily result in buggy code, where we all of a sudden realize that the customer has been charged for something they did not really agree on, and the final order details are not reflective of what is presented in the service agreement document. So that's a bug. Okay, so where is the problem here? How did this happen? The problem boils down to something we call non-determinism. And this sounds like highly theoretical or philosophical, so let's break it down a little bit. But when we say non-determinism, we mean any time we have a combination of parallel processing, which is not sequential, non-blocking, handling mutable state. So parallel processing plus mutable state is going to result in non-determinism or non-deterministic situation. So the Professor Rabbit is trying to explain here in 3 observations and trying to help us define determinism. What is determinism? The first observation says non-deterministic program cannot be fully testable using only deterministic testing. So right there, we are in kind of troubled waters, because if we cannot test our code, that smacks of poor engineering or sloppy engineering. Observation number 2 by Martin Fowler, the guru, states that non-deterministic tests have 2 problems. Firstly, they are useless. Secondly, they are a virulent infection that can completely ruin your entire test suite. So there's a deep trouble here with any lack of determinism in our engineering. And finally, observation number 3 is that non-deterministic programs are not fully testable. This is alarming because we have this bad news coming at us that a non-deterministic program is broken. And as software engineers, we are not comfortable. We feel uneasy about this situation because we don't want to be shipping something that is broken, something that we cannot test, something that we're just hoping and praying will work. That will not cause us any headache. So, to be more precise, a non-deterministic program without proper synchronization is broken. So what is proper synchronization? Basically, proper synchronization is just another word for synchronous processing, which is sequential blocking. And basically, if we are going to now say, okay, look, we need to synchronize these things, we're basically back to square one, back to where we started from, back to imperative, sequential blocking, and back to continuous execution. And it's like, okay, why expend all this effort and trouble just to find ourselves back to where we started? So this gets us to the end of part 3. And in part 4, part 4 will be the final part of this tutorial. We will look more closely into how to avoid shared mutable state, because that's the root of all evil. Also, we gaze into the perils of non-deterministic programming. Very troublesome, but we need to tackle it head on, and we need to find a way to reflect model reality as it happens in parallel processes, while avoiding all the pitfalls of using shared mutable state, avoiding pitfalls related to latency and inconsistent data. So until next time, I hope you will be able to understand why the trade-off between continuous execution and then avoiding blocking and hogging resources, switching over to discontinuous, but also recognizing the dangers and perils. Until part 4, I hope you'll have fun trying out various scenarios in your attempt to break the before-after blocks of code, switching over to asynchronous, and then finally in part 4, I think everything gets together in a completing the puzzle and hopefully helping us become rock-solid engineers. Until then, bye.